While they pull up the presentation, thank you, Maury. Let me reflect for a second, because I actually joined Caltech right when CAST was starting. And when I came to interview, they were talking about this new center that was starting, and I thought, that sounds exciting. This should be fun. So it all kind of started right when I began, and the energy that came with the formation of CAST. And Maury just showed all the achievements, but what's happened in these 6 years since CAST has happened has really been exceptional. The way it's brought together the campus, brought together the university, brought together people on research, and Maury has really been an incredible leader in this respect. So first and foremost, thanks to Maury for putting this day on and bringing us all together. It's not easy. It's not easy at all. And with that, I'll get to the technical bits. To kick off the next session, so as Maury mentioned, the key tenet of CAST when we were starting it through all these conversations was this notion of merging body and mind. And you know, you've seen a lot, of course, on AI, its proliferation everywhere. It's an incredibly powerful tool, but without data, it's nothing. And without the ability to take that data and take what you learn and put it on physical platforms, it won't be able to help us in the way that robots can help us right now. So really, this key challenge is how do we bring these bits together? And the first two sessions this morning are more on the body part, but there will be, of course, connections with the mind as well and how we instantiate autonomy. So we're going to talk about embedding autonomy this morning. That is, how do we take autonomy and put it on things like novel robotic systems? So to kick off, I'm going to rehash a couple of Maury's slides just to connect back up again. Again, the ultimate idea was to bring together bodies and minds and do this through ambitious moonshots, right? And this is more of a Mars shot, which is more the way I like to think about them now, is let's get things on Mars as well as the moon, as JPL indicated earlier. But how do we set these kind of seemingly crazy goals and then push the science to actually make them a reality? And as you saw earlier, CAST started with this collection of moonshots. And these have really stood the test of time over the last 6 years. You know, they kind of represent all the different ways you can imagine robots interacting with people, through partners, through the environment, through things like explorers, but also the ways they can help us through things like guardians. You know, wildfires were mentioned earlier. How can we have robots that serve as guardians? And so we've developed in each of these moonshots over the years. But something interesting, I think, has happened recently, and I think this marks sort of the next stage of CAST, which is it's not just the individual moonshots now, but we've started to think beyond the moonshots and how we can bring them together, how we can unify between multiple moonshots simultaneously, now that we have this sort of baseline capability. And this was one example. This was with the Raytheon project, where we brought together these moonshots, if you'd like. So it's sort of transformers in the sense that we have multiple robots here with different locomotion modalities. And they're able to work together and coordinate autonomously to explore a space. And so what you can do is utilize, you know, if there's rough terrain, you can use the light as a quadruped. If you need something a little bit rough, you have tracks. And then finally, you have a wheeled vehicle that might have most of the equipment on it. So how do we pull those together in the transformer context to explore a new space? And so this is this multimodal locomotion paradigm that JPL is thinking about for the moon right now. And this is, when I talk about combining moonshots, this is really, I think, a wonderful example. This is not my work, and Alireza will talk about this in this session. So I'm just highlighting really quick this idea of bringing together multiple moonshots. In this case, you have a transformer, and it was directly motivated. This is not my work, but I heard it's directly motivated by thinking about combining the Mars helicopter with the Mars rover. And now you have a platform that can go both fly and drive and transform between those modalities. So it can explore new and novel spaces by leveraging multiple modes of locomotion. And so this leads to kind of where we're going next in my mind, which is how do we really bring together a bunch of different robots and really fully leverage their capabilities? So as an example, this is one of our more recent moonshots now that we're just kicking off, and it's a result of TII. And in particular, we want to think about a robot that might be able to do more than just fly and drive, but also walk. So now these are just mock-ups. This is just an illustration of what this robot might look like, but you'll see in a second, these are more than just mock-ups. We've started to work on different components of this. And again, the moonshot here is how do we do this? Just at a basic level, what is the mechanical design needed? But the design itself is one thing, but we really need to couple that mechanical design with the software under the hood. So if we're going to achieve different modes of locomotion, we're going to need to leverage an autonomy stack really, really deeply. And so this talk now is going to talk a little bit about what it means to leverage autonomy stacks. And I have to say, as sort of a sidebar, this is, I think, the paradigm shift I've had since I've been a part of CAST. So when I got here to Caltech, I did nonlinear control on robots. And I had what I would call a very flat worldview. You know, I thought that everything would be a set of equations, and then you do your algorithms, you put it on the robot. And what I've really come to appreciate, that autonomy requires this three-dimensional viewpoint of the world. That is, you have to understand that any autonomous system is going to leverage different algorithms at different layers, at different time scales. And those need to communicate across those time scales. And that's the only way you can really get the full potential out of these robots. So I'm going to explain what this means, how we've leveraged it recently, and more importantly, how we use it on things like dynamic robots to achieve diverse behaviors. And so at a simple example, and this is actually not simple, this was sort of the state of the art just a year or two ago, if you would like. How do we look at autonomy just on a walking robot? And I won't go through all the details, but just this one mode of locomotion out of the three I talked about earlier itself has its own autonomy stack. So autonomous systems have layers upon layers, right? And so in this stack, to do things that this robot's doing right here, you have to do everything like make decision making. Where is the robot going to go? You have to plan its trajectories. That's its walking gait. That's like your spinal cord, your central pattern generators. And finally, you have to react in real time to disturbances in the environment that you didn't model or sense. And so right now, it's going to go over this root system that it didn't know was there, and it dynamically will react to it. So when you see this type of robust autonomous behavior, it's not a function of one algorithm at one layer. It's a function of taking all of these algorithms holistically together and understanding their interplay. And that's what has to be developed for any system to truly be autonomous, is layers upon layers of algorithms. And more importantly, at a scientific level, we have to understand how we can pull those layers together. So that's when the computer stops, which is always fun. All right, so what does this mean? Well, as soon as you start having all of these layers in an autonomy stack, safety starts to become critical. Safety is always critical in autonomous systems, but certifying safety becomes ever more complicated, right? Because you might have heuristics for safety at one level or another, right? If something bad happens, you stop an actuator here. If something bad happens, you do this. But if we want to do something like, so this is actually based on a DAO project with CAST, where we're in these are distillation column trays. So where you mix chemicals. And you might have regions where you can't go with the robot. How do you, with this complicated autonomy stack, and this robot's very complicated, we'll be talked about this session a little bit more, we need to avoid maybe a bad region. How do we understand what that means in the context of, again, these layered autonomy algorithms? And so that gets to this notion of safety. And so this has been sort of the central theme of my lab, which is how do we guarantee safety on autonomous systems? And so again, this seems like a thing that you can just apply enough algorithms, it's going to work, but it gets very complicated. So here, what you saw in this video up above was there's a big rig truck here. This was a collaboration with Michigan that I had. And on that truck, there was an adaptive cruise control algorithm. And it seemed to work, meaning the company that built the truck developed this algorithm that seemed to be fine. And what we did is we found a corner case, right? We found a set of conditions for this truck such that we could violate that algorithm. And so that's what this would be, is a crash. So the truck didn't know the van was actually offset by a lane, so it would have plowed into it. And the reason why we can find these corner cases, again, as you have these autonomy stacks with all these layers on them, people miss things. And all this gets clumped up, the edge cases happen, and failures occur. So the basic premise is what we need to do is take whatever was dealing in this software. We can't certify all of the software. It's too complicated. We can't go into the truck and find out where their algorithm failed. We could, but it takes a lot of effort. Rather, what we're going to do is after they run their software, we're going to do our software at a final stage before we put things on the actual hardware. That is, we're going to filter whatever they're doing to make sure that safety is always satisfied. And we can do that even for very complicated autonomy stacks. In fact, we can leverage autonomy stacks. And underlying all of this is math. And so again, I always say I'm required to have a theorem in every talk I give. So here's the theorem, the only one, unfortunately. But the basic idea is we can completely characterize safety mathematically, and through that characterization, know exactly what to put here to guarantee safety mathematically and in practice, as you'll see in a minute. And that gives us a guiding light, a guiding principle. I mean, things never work in practice like the math dictates, but the math tells you kind of what to do at a macro level. and more importantly, what signals to look at and what values to look at. And we can use that to guide the generation of this filter. And in order to successfully do this, we can't be complacent. We need to put it on lots of hardware to check the math as rigorously as possible, both theoretically but also in practice. So these are just some of the robots we put this on through the 6 years that CAST has existed. So this is just a subset of some of the videos, some of which you've seen earlier, including things like exoskeletons, walking robots. And so the more we put this on autonomous systems, the more we can understand where the failures might be, where we might not have thought of certain conditions that happen, and guarantee safety in a more seamless fashion. So let me show an example of this with air environment. So this was a CAST project from 3-4 years ago now. And so this is just to give you an idea of what this safety filter looks like in action. So in this case, the safe set is don't hit obstacles in the environment. And you have a drone here with onboard sensing, onboard computation, and a camera, so it's sensing the environment. And the pilot tries to drive the drone right through this obstacle. It's as if he didn't know that the obstacle was there. And this safety filter prevents the drone from going through the obstacle, and as soon as the obstacle is removed, the safety filter lets the pilot do what he wants. So at a macro level, this is what we want to do on all the systems. And you can do this in more complicated obstacle environments. So in this case, we have, again, more obstacles. The same thing applies. And importantly, what this gives is a certification of safety. So this plot here is telling us whether we're safe or not. And as long as this plot is positive, as long as these values are always positive, we know we were safe, so we have a certification. I should say, despite what's happening under the surface. So this drone was actually running complex algorithms developed by Air Environment, really good algorithms, but we could do this on top of their algorithms. We also can take this out into the field. So this is now a drone, and this is a high-speed drone, and here it's actually being dropped, meaning the pilot turns off all of the control signals, and we have a safety filter that prevents it from going to the ground, right? So this is called geofencing now. It's much like the obstacles you saw earlier, where we have a region in space that the drone can't cross. And the pilot might be trying to fly the drone out of those regions, but we can actually put up a barrier. So we're working right now with actually TII and thinking about this in a security context on swarms of drone robots. How can we use these ideas to understand security? But again, this is what it looks like on this high-speed racing drone. And the important part is we're doing this on board with onboard sensing, onboard computation at 100 kilometers per hour. So this is very, very high speed and timing critical, if you'd like. So this is this transition to practice. So how do we do this transition to practice on these complicated systems? Again, I mentioned the autonomy stack, and so far I haven't really talked about it. But the way the autonomy stack works is it not just gives you, it's not just something you might want to filter on the back end, but it's something you can actually actively exploit to make safety guarantees on the system without necessarily understanding what's below the hood. This was the paradigm shift for me. Again, as a control theorist, I always wanted to know sort of the full dynamics of the system. But again, with complicated autonomous systems, you won't know. You just won't know. So in this case, we have 2 quadruped robots. Those are actually being run by algorithms developed in my lab, walking algorithms, but these are very complicated walking algorithms. And in addition to those walking algorithms, we pin the robots together. So that makes it even more complicated. And what we say is, on top of all of that, we want to ensure safety. And the way we do that is with this safety filter idea to avoid these obstacles. So how do we do this on these complicated systems? Well, we can actually, again, like I said, leverage the autonomy stack. So at a basic level, think about when you're joysticking a drone, if you've ever flown a drone, or just driving your car. When you're interacting with your car, you're turning the wheel and you're hitting a couple pedals. That's the only interaction you have with the car. You don't understand the dynamics of the car. You don't know that the control algorithm is running at the engine level, right, to regulate speed. You're able to successfully avoid obstacles in the environment, hopefully most of the time, right? And so this same idea we can do mathematically now. So we can modulate the reference signals going into the system. Meaning in this case, we have the exact same safety filter running on a drone and on a quadruped. And all we're doing is modulating the reference signals, the desired signals going in, with these safety filters, and we can actually mathematically guarantee safety even in this case, even though we don't know what's happening below the hood. So this is kind of the basic premise that we're starting to build on to get to much more complicated autonomous systems in practice. So we've had success with this and then layering it even further. So I'm just showing it a couple examples now of how we could take these ideas and pull them even further up the autonomy stack. So at the basic level here, we have a bunch of different walking algorithms. And below the hood, we have really complicated nonlinear control algorithms. But at the top level now, we have this planning layer that we can start to instantiate through our understanding of this autonomy stack. So what's happening here is as this robot walks over this terrain that it never saw before, you can see on the right the way it switches between these different motion primitives in a dynamic way to recover. So again, the way to autonomy is leveraging the autonomy stack. By knowing that under the hood we have all this capability, we can plan through that capability in a safe way. In this case, the robot didn't know it was going to get picked up and thrown. It picks itself back up. So my premise is that autonomy is really the collection of very good architectures in the control system and mathematically understanding it. Again, going back to that safety filter and how or I should say one more thing, you're going to see a talk on this later, but we're doing this, for example, on this Dow robot, where we have perception, we have the motion primitives, and then we have complicated behaviors under the hood, like transitioning between these different levels of the tray to realize autonomous behavior. But again, going back to this safety filter idea. Okay, so I mentioned this safety filter. We have all these layers, and now we want to bring it together and ensure safe behavior. Again, just to show how this works when you start to have uncertainty in the loop, is now imagine you have a vision system. So with that vision system comes uncertainty, in this case on depth. So we want to not hit obstacles in the environment, like the tree or that chair, or in this case a person. We can take those depth estimates, put those into an uncertainty bound in our safety filter, and be robust and modulate with respect to them and still guarantee safety. So here the robot is sensing the person, not hitting the person, and then as the person comes closer, the robot steps back. So you get this sort of emergent behavior by enforcing these safety layers. And you can do this in very complicated dynamic ways. So this is going to be discussed later today, so I'm just going to show a video. If you don't take into account this uncertainty, what happens? Right? So in this case, the uncertainty was the bottle. It didn't know it had a bottle attached to it, and of course, it's going to crash pretty dramatically. On the other hand, if you account for the uncertainty, in this case, we use learning to learn the uncertainty in the safety filter. So it's very structured learning. We're able to ensure safety. Even though we don't know about this mass, we don't know the dynamics of the hanging mass, we can get this system within a couple centimeters of the ground. So again, we're able to leverage the autonomy stack and ensure safety. And this leveraging allows us to extend it to a variety of different application domains. So as a recent application, we applied this same idea that you saw with the drone to an exoskeleton. So this is a lower body exoskeleton, and it's able to walk dynamically, even with these multi-contact behaviors, through this safety filter idea. So this gets to the last bit, is where are we going next? And I'm really excited about, all throughout this presentation I indicated the sponsors, and we have a lot of exciting projects happening, but one that I'm especially excited about, I should say, is we're starting to think about how this safety filter idea can be leveraged in the context of building robots, not just controlling robots. So we want to really take this to a next level. And so what we can do is view software, that is our ability to generate walking gaits, as the nominal. And then we can use co-design as our safety filter, meaning we design around this software to ensure optimal and safe behavior on the actual hardware that we instantiate. So we can create a feedback loop such that we can modulate the mechanical design and get optimal designs out that are also guaranteed to satisfy the properties we care about. And we did this on this robot. So this is the final result of this algorithm, and this is the physical robot that we built to instantiate those ideas. And we can test this out now in practice. So this is actually the first walking on the Caltech humanoid robot, the Caltech cast humanoid robot. And so it's able to dynamically walk, dynamically balance itself, and importantly, it was designed with this optimal purpose in mind, right, of walking safely. So I want to just watch it for a second, because I'm always excited when there's a new robot walking. And again, these are just the first steps taken by this robot, and this is all very recent. But our ability to go from a design to a dynamic realization on the back end is very exciting. And as I mentioned earlier, we want to bring this together. This is step one of many steps, no pun intended, to building even more capable robots able to do even more. So earlier on, I told you about this idea of having a flying, walking, driving robot. And in this case, this is the walking bit that we're starting to develop. The flying bit you already saw with M4. And so we're at a point now where we can start to think about combining these different capabilities together. So that's where we're at, where we've been, I should say, some of the achievements we've had, and you're going to hear more details throughout the day. But more exciting, I think, is really where we're going, what's on the horizon. Again, the ability to leverage autonomy stacks, to think about guaranteeing safe behavior in the process, to develop new hardware platforms and then bring those platforms out into the real world to do really fun and dynamic things. So there's an exciting future on the horizon for CAST, and with that, thank you very much for listening. So next, Alireza is going to talk. So now, the way these sessions work is there's a bit higher level presentation, and we're going to deep dive in a couple of the specific instantiations. And the first one is the M4 robot and our newer multimodal robots that we're developing here at Caltech in collaboration with Alireza from Northeastern University. So I'm excited for him to talk more about the robot, dynamic robot side, especially M4. So Alireza, take it away.
Yeah, thanks, Aaron. Yeah. Thank you. Before I start my talk, I just want to see if I can acknowledge the hard work of our students, both on West and East Coast. We have a fantastic team of researchers at CAST, JPL, and Northeastern in Boston. The way I define myself and my research, I have a keen interest in designing morphing machines that can dynamically interact with their surrounding world. And my primary research focus to harness their interactions to achieve efficient, resilient, robust translation of center of mass. I mean, as far as hardware design, I use soft rigid body designs. For controls, I use nonlinear model-based control design techniques. I'm not really obsessed about any specific control approach or hardware design approach, really taking the approach that best aligns with the objectives and goals that I have in mind. My research is greatly influenced by BAT's morphing capabilities. We refer to this as dynamic morphing wing flight. While many of you wonder why I don't draw inspiration from other animals with morphing bodies, bats have unique capabilities. They can, despite their small body size, they can mobilize many active, passive degrees of freedom, and they can dexterously manipulate all these movements. This is quite impressive. This is not a random movement. I call it dancing in the air. And there is another great characteristic here, and that is they can perfectly integrate posture manipulation and thrust vectoring, meaning they can regulate, they can manipulate their body shape, and they can regulate the way their body interacts with the surrounding world to extract the force that they need to push their body in a specific desired direction. So this has greatly influenced my research, and that has led to sort of quite a bit of bio-inspired designs within my team. We have created drones that look like bats. They can dynamically morph their body structure, and they can sort of produce thrust to weight ratio that is enough to carry a camera, a powerful computer, while avoiding producing powerful and continuous air jets, which enables them to fly inside extremely confined spaces, channels, HVAC channels as small as 2 by 2 square feet in cross section. So we are interested to use these machines for remote sensing in future. We also create custom designed dynamic walkers with literally jetpack attached to the torso to further delve into the concept of posture manipulation and thrust vectoring in the context of legged and terrestrial locomotion, with application to locomotion over steep slopes, inspired by birds, wing-assisted incline walking and running. I'm going to briefly talk about it when I give you an update on M4. We also look into locomotion systems with manifold moving joints and contacts to enable traversal over rough terrain and aggressive environments. These are high-dimensional problems, and classical methods fail, or they are not efficient. We use ML-guided control techniques. And here, the goal and the objective is to really operate in environments where classical standard mobile robots such as wheeled systems or legged systems face the risk of complete immobilization. So this is sort of briefly speaking what I do when it comes to designing morphing systems. Then M4. In 2021, I started collaborating with CAST and JPL, and that was sort of the time that the idea of M4 was conceived with Mori and myself. And basically, the whole idea of posture manipulation and trust vectoring is pursued in M4's design. However, we have a different objective here. The objective is to significantly enhance locomotion plasticity. And by that, I specifically mean that we want a single platform to showcase many different modes of operation. So that's the whole idea here. This project, as I said, started 2021 under Mori's leadership and with a funding from Jet Propulsion Lab. And Mori, myself, and JPL's Arash Kalantari, we aspire to use M4 for Mars explorations one day. We are working hard to that goal. I'll give you a brief update in that regard soon. But there are several unorthodox designs in the past years trying to sort of integrate posture manipulation and trust vectoring to create machines, multimodal machines. How M4 is different from these solutions? If you inspect these multimodal systems that are out there in the literature, they cannot showcase more than 2-3 mode of operation. And those of us who do design, we know that when the modes of operation increase, each mode of operation introduces its own conflicting requirements. And accommodating all these conflicting requirements is not a trivial task. So in M4's design, we took the following design philosophy. We considered multi-purpose appendages, and we attached these multi-purpose appendages to a morphing structure. Basically, with this, we try to extract different functions from the appendages and with the morphing body to be able to realign the system, realign the appendages to maximize the performance. So this is UGV to UAS transition. So the appendages are repurposed from wheels to thrusters. And we have a smooth transition here. And making a transition from UAS to UGV. That's what's happening next. As you can see, this is almost instantaneous transition that makes basically M4 very suitable for scenarios where multi-phase scenarios when we want to make quick transitions between different modes of operation. This is mobile inverted pendulum mode. The front appendages are repurposed to thrusters to lift the vehicle, while the rear appendages are locked to balance the system and go to mobile inverted pendulum mode. This is also good for scouting if you want to do the scouting, increase perception performance from high vantage point. We also looked at MIP maneuver to go over obstacles that cannot be managed with wheels. So the front appendage is repurposed to thrusters, realigned to maximize the performance, and the rear appendages push the vehicle towards the obstacle. It's going to happen in a few seconds. And then once the obstacle is cleared, the system sort of goes back to UGV mode and continues the mission. As you can see, this is a very interesting combinatorial problem. So, depending on what are various functions that you want to extract from the appendages and how you realign them, you can get different modes of operation. And this is clearing the obstacle and going back to UGV mode and continuing the mission. We also use this mobile inverted pendulum configuration to traverse over steep slopes. And this is the maneuver that will show up next. So So birds can use their flapping wings to generate aerodynamic forces to sort of increase traction force to traverse over steep slopes. And we were inspired by this maneuver of birds, and we used the thrusters, the top appendages, to produce force and manipulate contact forces and traverse the steep slopes of up to, this is 30 degrees, but we could, this is 45 degrees, so this is not possible with UGV mode, and we use the MIP maneuver to go over 45 degrees steep slope. So as you can see, M4 can showcase different modes of operation. As I said, this is a very interesting combinatorial problem, and there are so many other operations that we have not yet explored, and we are interested to explore it. This is certainly a very exciting aspect of M4 project, the number of modes of operation that we can get from M4. But in my opinion, the other exciting research avenue here, it's autonomy. So M4 can multifold its thrust to weight ratio without any single added mass. And that gives us a payload capacity or surplus payload capacity to carry like computers and powerful computers for autonomy. And this is another interesting aspect of M4 project here. We put these blocks on M4's pathway, and using its onboard computer and suite of sensors, it fully autonomously decides how to switch from UGV to UAS mode and clear the obstacles. So on the right-hand side, you see the point cloud information on the occupancy map that the system forms in real time to resolve this multimodal path planning problem. So this is a facet that has been initiated. We are striving to take M4 to outside CAST and participate in real-world operations. And for more updates on this, please stay tuned, visit CAST website, and thank you very much.
Next up is Peter, who works with Nima and Maury. Take it away.
Hi, everybody. Yeah, so thank you. I'm a postdoc who works with Maury, and this work was done in collaboration with Nima's group, and it's called Fourier Adaptive Learning and Control for Safe Flight. And so, kind of as a lot of the session has talked about, we're kind of inspired by nature, and specifically how robots interact with fluid mechanics. So if you look at the problem of flying in a city, just around a single building, you have things like updrafts, downdrafts, shear layers, and vortices, all of which can result in basic disaster for a drone trying to fly through them. And they're especially problematic for fixed-wing drones because those same aerodynamic surfaces that allow for efficient flight basically serve as surfaces for large disturbances to take strong effects. Now, birds don't really have this problem, and so here we have some kestrels hovering, and if you look at the head of this bird, specifically when I play the video, you'll see that it's perfectly still, and how much it's actuating its wings, despite being on a rocky sea cliff face. And so here we have a different angle of the same bird doing the same behavior, and we see, A, that there's a lot of frequency kind of going on. There seems to be some kind of fundamental frequency, which agrees with what we know about the physics, and B, its feathers are moving a lot. And so this is because the birds can actually use this motion of the feathers to sense the fluid mechanics around them. And so other birds, specifically of the Priscilliform family, which are large seabirds and some of the most successful flyers, they have these tubular-shaped nostrils, which actually serve a lot like pitot tubes, as you find on an airplane. And so this enables this really unique dynamic soaring behavior where they're able to fly something like 500 miles a day, flapping very little. So returning to the problem of drones quickly, we wanted to basically address the issue of flying in a city or a really complex fluid environment, but we first needed to reduce it down to a 2D problem. So we have a basic symmetric airfoil with a trailing edge flap, like on an airplane. If we point the flap down, we get lift in one direction. If we point it up, we get lift in the other direction. We mount this system on a load cell, and we put it behind a large bluff body, which creates disturbances. Here we have it in our cast wind tunnel, and you can see there's a lot of turbulence. We also integrate flow sensors, because like we were talking about, this is kind of the sort of information that biological flyers use to make these advanced control decisions to maintain stability in really turbulent environments. So the actual experiments that we are going to see here were performed in the Lucas wind tunnel. And instead of this symmetric cylinder that we're seeing up top, we actually used an asymmetric bluff body, which was dynamically mounted on bungee cords. So there was a lot of different frequency content. And here we actually have the power spectral density of the flow. And we see that there's a lot of low frequency dominant energy in the flow, which essentially means that we're not expecting to see a single peak or anything that would be really clean and easy to predict. It should be a pretty challenging problem. And so now I'm going to introduce kind of our solution on the algorithmic side of this, which is the FALCON algorithm. So the FALCON algorithm has two parts. First is a warm-up. So here we basically need to take just a little bit of data to essentially build a basis in frequency space on which we'll actually learn the flow and the dynamics of the system. And so kind of the clever part of this is instead of trying to model it through brute force with a neural network or something, we're basically performing least squares on a Fourier basis. So we're taking a very nonlinear phenomena and we're using a nonlinear transformation and then modeling it linearly. And so we use lasso regularization while we're performing this to create a sparse basis of frequencies. And then we just run this again and again, and this allows us to use pretty much a plug-and-play controller, cross-entropy method to make our predictions and our actual control decisions, and we're able to update our Fourier basis pretty quickly. So we compare this to 3 model-free reinforcement learning algorithms. Here, FALCON's in purple, and we don't run it for nearly as long because it doesn't require nearly as much data. And we see that here we're plotting the standard deviation in the lifting force, and we see that FALCON significantly outperforms all 3 of the cases, even with, again, far less data. And if we plot the mean lift, we also see that it achieves a really solid, consistent mean lift with only around 40,000 samples, where with 160,000 samples, the other methods still fail to really achieve constant lift. So next, we're kind of looking to push this project forward with a new generation of students and postdocs, and we're trying to bring it into real world with 3D flight. So we're trying different methods at the moment of kind of platforms we can use so we can actually fly in the wind tunnel, which is challenging even with expert pilots and no learning. So yeah, that's what I have. Thank you.
He's going to shift focus a little and talk about 5G. Take it away, Shawn. Thank you.
So good morning, everyone. My name is Shawn. I'm an electrical engineering grad student in Professor Azita Amami's lab. And today I'll be going over our work on experimentally characterizing atmospheric effects on 5G, 6G signals, as well as millimeter wave propagation. So the motivation for this work is that atmospheric effects on electromagnetic propagation is not very well understood, especially for frequencies above 50 gigahertz. This is really important for applications like 5G, 6G, and beyond, as the push to higher frequencies in the electromagnetic spectrum allows for faster speeds, larger bandwidth, and lower latency. It's also important for applications like UAV and satellite systems, as well as radar and remote sensing. So the goal of the project is to try and develop a statistical channel model as a function of atmospheric conditions in order to better understand the physics of propagation. For a communication link between a transmitter and receiver, the channel can be modeled as a moist, turbulent, clear air medium. And the electromagnetic wave experiences scattering, refraction, and diffraction, which results in scintillation at the receiver, which is the random fluctuations of amplitude and phase. And this is caused by changes in the refractive index due to temperature and humidity gradients. However, the challenge in characterizing these effects in the lower troposphere is that it requires a lot of manpower and capital expenditure to establish a line of sight propagation link over large distances. And furthermore, naturally occurring turbulence is very unpredictable, and in order to characterize it, we would have to establish many in situ meteorological sensors placed along the propagation path. And so we would like to try to shrink the setup by utilizing the cast fan array wind tunnel in order to generate turbulence in a more controlled and predictable environment. This greatly simplifies the experimental setup and keeps things more consistent. So we utilize a 95 gigahertz Doppler radar in order to generate this millimeter wave beam. And it is in a super heterodyne architecture, which allows the minimization of the effect of the system-induced noise as well as phase noise from the electronic components. And we are trying to analyze the statistics of the received signal in order to determine how the turbulent flow caused by the fan arrays affects the actual propagation itself. So this is a picture of the overall experimental setup where we have heaters placed in front of the fan arrays in order to generate a large temperature gradient. And we also have like IR cameras and thermal screens in order to determine the temperature of the flow, as well as hygrometers and anemometers for humidity and wind speed measurements. As a sanity test, we first did some initial measurement results to verify that the phase noise introduced by the electronic components are minimized so that we can increase the ability for the effect of the scintillation caused by the turbulent flow in order to be able to be measured and characterized. We also measure several meteorological parameters like pressure, temperature, humidity, and wind speed in order to be used in our theoretical models that we can verify and expand upon. Here are some comparisons between the theory and our actual experimental results. Although these two plots don't lie exactly on top of each other, we can see the general trend of how the mean wind speed affects the measured results due to the turbulent flow. As we increase the speed of the fans, it pushes the effect of the turbulent eddies towards higher frequencies, which is consistent with the theoretical models. And so this is just one type of measurement that we have to try to expand upon these theories. So in summary, we have implemented a novel experimental setup for studying millimeter wave propagation in using the cast fan array wind tunnel. And we want to continue with improvements towards a more sophisticated suite of experimental procedures, and then use this data to develop a statistical channel model that can be scaled towards real-life applications. Okay, thank you.
Thank you, Shawn. Next up is Preston. And just a reminder that after this, we're going to have a poster session during the break. So if you have any questions, that's a great time to go find everyone giving these presentations and do follow-ups.
Perfect. So hi, everyone. My name's Preston Culberston. I'm a postdoc in Aaron's lab. And today I'm going to talk about some of our work on using generative modeling to do stochastic safety. So the problem that we've been thinking about is actually safety under uncertainty. So oftentimes when you're running an autonomous system, you often can't exactly model what the dynamics of the system are. There will be unexpected disturbances or uncertainties that are coming from your perception system. And so what we've been interested in are ways that we can actually be safe despite that uncertainty. So this, we've actually seen a video of this experiment already, but what we have is a quad-rotor drone where we want to enforce some safety constraint. So this is basically the floor, and we want to obviously keep the drone from hitting the floor. But what we've done is we've actually tied this unmodeled disturbance to the drone. So this is a bottle that weighs actually about half the weight of the drone. And we are actually not giving the drone any information about the payload. So it gets no knowledge of where the payload is. It has no knowledge that the payload's even attached to it. All it knows is its own dynamics. And so if you run a kind of standard safe controller, what you can see is this crash video we saw before, right? You can see actually that the leg breaks off on the bottom. When you have a huge unmodeled disturbance like this, obviously your safe controller is going to fail. And so the question that we asked with this project is how can we guarantee safety even when we have uncertainty about our dynamics? So the approach we took is kind of two steps. The first was to use a tool called deep generative modeling. So this sounds very technical, but I would guess everyone in this room is somewhat familiar with this concept. If you've used something like ChatGPT, right? So I just prompted it with something like draw a picture of a drone with a Gatorade bottle. It's able to generate images like this, like actually surprisingly well. And what's interesting is actually the technology we use for this project is the same as what underlies ChatGPT. So by prompting this, ChatGPT is able to generate random images that kind of correspond to the input that we provided. The idea for this project was to use a similar tool to ensure safety on board an autonomous robot. So what we did was actually we collected training data. So we collected about a minute of drone flight with this unmodeled disturbance. And then we use a deep generative model to actually generate a stochastic model of the drone with this uncertainty that's invoked by this unmodeled load. And kind of a key idea that I want to get across is that actually we structured this learning problem quite cleverly. So actually the neural network isn't completely modeling the dynamics of the drone end to end. Actually, all it's doing is modeling residuals of the dynamics about what the model-based, like physics-based model of the drone would be. And so that actually makes it a quite easy learning problem that, again, is based on this idea of deep generative modeling. The second thing that we did is actually we needed to come up with a new idea of how we can do safety for stochastic systems, right? So if you think about this like unmodeled slung load problem, actually this disturbance, if you can't sense the bottle, is effectively random. And so what we needed to do was think about how can you enforce safety mathematically for systems that actually have random dynamics. And so what we did is actually we went from a view of safety where you want to absolutely for sure keep your system safe to a probabilistic view of safety. So we want to enforce basically a chance constraint. Over some horizon, we want to keep the probability of the system being safe greater than 1 minus epsilon, where epsilon is some small number. And basically what we did is we generalized control barrier functions to a stochastic setting. And using a CBF-based controller, what we showed is that actually you can give rigorous safety probabilities for your system. And so the kind of control architecture that we proposed combines these two tools. Yeah, we need a safety filter for PowerPoint. But basically, what we're watching side by side, so on the left is this generative model combined with the stochastic CPF. And on the right is actually just a vanilla neural network that's trained without any sort of uncertainty or stochasticity. And what you can see is that actually our model is able to keep the bottle like very aggressively, but like very close to the ground while ensuring safety. Whereas this other baseline method where you just train a non-stochastic model, even though it's better than obviously not modeling the bottle at all, is still, still getting quite large safety failures. We're seeing the bottle essentially drag the ground. So in conclusion, what this project showed is that by combining tools like deep generative modeling, so kind of advanced AI techniques, with things like stochastic CPFs, which mathematically ensure safety, we were able to get performance to ensure safety on a system that had a huge, very difficult to model disturbance. And so I just want to thank my collaborators as well as our sponsor, BP. Thank you so much.
Great, thanks Preston. And then the last talk of the presentation is from JPL, our JPL colleague Arash. Him and I have been working together for years now. It's been a lot of fun, and he's going to talk some more on robot inspection. Take it away.
My name is Arash Kalantari. I'm a robotics mechanical engineer at JPL. Going to present our work with Dr. Ames on robotic inspection of distillation columns. Distillation towers need periodic inspection to check for any signs of damage inside, but this is a very dangerous and tedious task for human operators. Our goal has been to replace this with a robotic system to be sent inside the tower to do the inspection semi-autonomously. The concept of operation would be that we have an operator station outside of the tower where the robot is going to be set up and deployed inside, connected to the operator station through a tether system, and then go inspect all of the trays inside the tower by a map that or waypoints that the operator introduces to the system. Once inspection on a tray is completed, the data is sent back to the operator, and once the confirmation is given to the robot, it can proceed to the next tray. And this process is iterated until all of the inspection is completed and the robot is retrieved from the tower. As you can see here, there has been different pieces to this project, from mechanical system and mobility to motion planning and control, perception system and navigation, tether system and user interface, that our teams at JPL and Caltech have been working very closely on different pieces here to make this system work successfully. But to begin with, given this quadruped system, which is very capable to walk on a single tray, how do we enable it to transition between these towers that come at different specifications? So we did go through a lot of different ideas in our brainstorming phase, and we ended up with, given all of the constraints that we had, we ended up with this solution that we call roller arm. It's a 4 degree of freedom robotic arm that we have specifically designed for this task that gets attached to the quadruped robot. We did go through all of different steps here, from concept design to mechanical and mechanisms design, and then doing a single prototype design, going through simulations to optimize and validate this design, and then eventually fabricating and putting together all of the mechanical and electronics. After that, we, by doing offline motion planning and doing dynamic simulations and implementing on the actual hardware and running experiments, we could optimize our motion primitives to be able to efficiently transition up and down between these trays. Another important piece for us was our tether system, which provides power, communication, and mechanical support to the robot and between the operator station and the robot. This system is decomposed into two spools, the longer spool, which goes between the tether system or tether pod and the operator station, and the second part, which is a shorter segment and goes from the tether system to the robot itself. Our autonomy architecture is illustrated here. We go in with an assumption of having a prior map of the structure inside. Our localization system, using the sensors that the robot has, and this prior map can locate the robot on a single tray. Perception system can do our traversability analysis and detect the dangerous areas for the robot to avoid. And then those are fed into our planning system, which can plan the best path for the robot to get to the inspection targets. And all of these can be controlled by the operator through our graphical user interface. The commands are communicated to the robot and the low-level controller of the robot, which controls all of the motion primitives, including the transitions or walking on trays or other behaviors that the robot can have. You can see in this video an example or an experiment where the robot is commanded by the operator to navigate on a tray to go to a specific target positions. It can use all of these subsystems to successfully navigate around, avoid all of the risky areas, and get to the target positions and gather the data that is required. This is also the view of the operator. Looking at the graphical user interface, it can monitor the status of the robot and receive data back, send commands to move the robot around, and monitor the whole mission. Here are also some videos of the successful transition of the robot up and down inside the tower. You can use how the robot is using the degrees of freedom of the arm that is attached to it to do this successfully. We'll be happy to answer any questions during the poster sessions. Please stop by. Thanks.